This is chapter 18, and we're going to be doing the practice problems for the chapter. So we start off with some acidic conditions, right? So which of the following hydrogens is the most acidic? Alright, so the way I like to work this is kind of like common sense and can I form an enolate? Okay, so common sense is, why would 5 and 4 be right? See, this doesn't make any sense. These are just normal hydrogens right here, okay? And so they shouldn't be acidic. We don't have anything special going on, right? So we know that 4 and 5 are wrong because those are just normal hydrogens. They're not next to oxygens, not next to like phosphorus or magnesium. It's just normal hydrogen. So we know those are wrong. So it only leaves us with 1, 2, and 3, right? Okay, well, what I mean by can I form an enolate is, well, if I could form an enolate, that comes from an acidic hydrogen. Okay, so you're probably wondering what an enolate is. Okay, so essentially an enolate is something like this. Right, so we have a alkoxide, and then we just add a double bond right there. Or it could be right here. Right? That's an enolate. Okay, so can I form that? Well, notice that we have to form an enolate from a carbonyl. Can I form an enolate with an ether? Or at least an ester? No. So this wouldn't make any sense, would it? No, it wouldn't. So 2 is wrong. Does 1 make sense? If I can form an enolate like that? No, that doesn't make sense either. So 1 is wrong. What about 3? Well, what if I removed a bond, so we only have 1 bond to oxygen, and make that an alkoxide, and then I did this, right? So essentially, you made this compound, and we have like some other stuff attached to the right side. So basically I made this, and look at that, that's an enolate. And so whenever you're asked to find which is the most acidic hydrogen, the answer will be, if it could form an enolate properly, with like the proper bonds and there's no excess amount of bonds, then it was the most acidic hydrogen. And so we can say that for number 1, our most acidic hydrogen would be right here. Okay? It would be on number 3. So we could say the answer choice is C. So, must form enolate. Must form enolate. Okay? Because the enolate's like an intermediate, and then it does more reactions, as you'll see in question 3. Okay? So number 2, what is the most acidic hydrogen? Okay, well, we know right off the bat that we have to form an enolate. Okay, that's like a key component. So I know number 2 is wrong because if I have a double bond right there, that won't do anything. There's no oxygen near it. Okay, so number 2 would have to be wrong. And what about 1? Again, there is no oxygen near it. So even if I put a double bond there, that wouldn't do anything for me. In fact, if I did that, this carbon would actually have 5 bonds. So we know that's not possible. What about number 4? Well, if I did that, that's not really going to help. That's not an enolate. Okay, so this is also wrong. And number 5, the same thing. There's no oxygen near it. Why would I form a double bond there? Okay, what about number 3? Well, if I did number 3, and we're just gonna kind of like ignore everything else. So if I did this, okay, well, I could form an enolate by deleting a bond to make this an alkoxide. And then this hydrogen right here can actually leaving the electrons, and those electrons can make a double bond. So as you can see, that is an enolate. We have a double bond next to an alkoxide. Okay, and this carbon would have 4 bonds, which is proper. Okay, So if I try to form it right here, well, this carbon would have 5 bonds, so that's why we didn't do it on the right-hand side. Also, there are no available hydrogens to begin with on the right-hand side. So the answer choice would have to be, again, C. Number 3, what would be the major product of the following reaction sequence? Alright, so you're probably wondering what we do first. You're probably saying, okay, well, we're going to do an SN1 reaction. We're going to add this water molecule to this carbon right here because it's like partially positive or something. But that's not true. That's not right, okay? Actually, this is going to be an acid-base reaction. So this is the acid-base reaction. And the reason why it's an acid-base reaction is because acid and bases react really quickly, and so it's going to want to do the first step really quickly, alright? So it's really quick. Really fast. And if something is fast, you're going to do it first. So the way this happens is that this guy right here actually it's going to take out a hydrogen from the acid. So this goes like this. One of these bonds break out. This oxygen takes the hydrogen. Alright? So when that happens, we get this product. And notice that we have 2 hydrogens on this carbon, right? Well, now the water is really angry because a hydrogen was taken away, and it wants to have its hydrogen back because we're going to reform the acid. So what that happens is that one of these hydrogens will be taken out and be placed with this oxygen. Okay? So now we have this. We have some lone pair of electrons and a hydrogen, and we also have our acid. Okay, so now after that happens, one of our bromine molecules can actually come in and attack. So our bromine cleaves off, and these electrons actually attack the bromine. And we have this. You're probably wondering, okay, but what about our hydrogen? Well, what happens in our hydrogen is that there are some electrons right here, and so these electrons can come back in to make a carbonyl, and this hydrogen can get, it can pop off, alright? And this bromine can take that hydrogen. So all in all, we would have this compound. Alright, or we would have answer choice A. Alright, so answer choice A would be the correct answer. Alright, number 5, you added the bromine in the wrong direction, and you also have an alcohol. This is not true. Number 4, you don't have any oxygen. Number 3, you added the bromine in the wrong direction, and same thing for 2. Okay. So for this reaction, whenever you have a ketone, a halogen, and an acid or base, you're going to do an acid-base reaction, and then you're going to try to reform your acid by taking this hydrogen. Now, the reason why we take these hydrogens is because they are more acidic. Again, we can make an enolate from that hydrogen. So if you can make an enolate from that hydrogen, you can actually give that hydrogen to reform the acid, and then your bromine can attach to the carbon. Number 4, Malonic Ester, aka diethylmelanoate, is treated successfully with sodium ethoxide, 1-bromopentane, potassium tert-butoxide, iodomethane, hot aqueous sodium hydroxide, and hydrogen chloride, and heat. What is the final product? So that's pretty disgusting. That's a lot. First of all, they gave you a substance that you don't know how to draw, most likely. So we have to draw Malonic Ester, and I actually drew it out for you right here. So this is a type of anhydride right here. Now if you notice, this compound would be the ester portion. Okay, so this is like the ethyl. So we have methyl, ethyl, and then we have an oxygen right there. So that's very typical for these types of reactions, and you'll see why in a couple of minutes, why this is very important. So when we treat it with sodium ethoxide, we are actually converting this portion of the compound. Okay, so that is going to be the ethyl portion right here. And so what sodium hydroxide does, so what sodium ethoxide does is that it removes these ethyl groups, okay? And what it changes it to is a carboxylic acid. So whenever you treat a compound that has this structure with the oxygen with an with an ethyl on it, you're going to make a carboxylic acid. So here's going to be my new compound. And again, this only happens because we treated the compound with sodium ethoxide, right? This doesn't work if it's like oxygen with 3 carbons or 4 carbons. No, it only works with ethyls. So only works with ethyls. Okay, so there we go. And now we're actually going to treat this with let's see here. Also, I just want to say that whenever we treat this compound with sodium ethoxide, you actually remove a hydrogen as well. So we had 2 hydrogens right here, and this is a very strong base, so it's going to rip off 1 hydrogen and just leave the electrons right there. Okay, so that's what we have. Now we treat it with some 1-bromopentane. Okay, so whenever we have 1-bromopentane, we have this. So 1, 2, 3, 4, and 5. Then we have a bromine. This bromine leaves, making this one positive. Now these electrons can actually take out this carbon. Okay, so now here is our compound. We will have something like this. Then we have 5 carbons, so we go 1, 2, 3, 4, 5. Okay, now we treat this with potassium tert-butoxide. So potassium tert-butoxide is kind of cool, I guess. So let's call it butox. And what it does is it's very sterically hindered, so it's a big bulky base. And when it's a big bulky base, it's actually going to take out a hydrogen. So it's going to take out this hydrogen that we have here, right? And it's not going to add anything, it just takes out a hydrogen. The reason why it doesn't add anything is because it's already too big and bulky. It's not going to go inside like the nooks and cranny of the compound. It's just going to take out a hydrogen, right? So this hydrogen leaves and leaves its electrons, and this tert-butoxide takes that hydrogen. Okay, so here we have this guy. Okay, now we treat it with iodomethane, and this is a pretty simple reaction. So we have a methyl and an iodine, and now this bond breaks towards the iodine, making this one positive, and these electrons can take out this carbon. Okay, cool. So this is what we have. One, 2, 3, 4, 5, and then we have a methyl. And now we treat this with heat. Now, you treat it with heat and some sort of acid, okay? So now what we form is that we're going to eliminate a carboxylic acid. We only do it once, okay? This forms CO2, so let's say that we do it on the right-hand side, okay? You could have done it from the left-hand side. I just like the right-hand side more. So we're going to eliminate a carboxylic acid, and we do this because we heated it up, okay? And whenever you burn something, you release carbon dioxide. This is a product of the reaction. So we have this guy. So we still have one carboxylic acid to work with. We go to this carbon. This carbon has a methyl on it, and this carbon also have 5 carbons on it. So we go 1, 2, 3, 4, and 5, and plus CO2. So we have CO2. And that CO2 came from the right carboxylic acid. So that formed a CO2. Okay? And so what is our answer choice? So our answer choice, it should be A. So let's count. We go 1, 2, 3, 4, 5, 6, and 7. Okay, so we know it's heptane something, but there's a carboxylic on it, so the heptane becomes heptanoic. The oic means carboxylic acid. So we have heptanoic something, and on the second carbon we have a methyl group. So it is a 2-methyl heptanoic acid, okay? So there we go. The answer choice should be A. So let's do a quick recap. Whenever you treat an anhydride with sodium ethoxide, you're going to remove the ethyl groups from the oxygen, and you're going to make a carboxylic acid, okay? Afterwards, with the same sodium ethoxide, you're going to remove an acidic hydrogen, alright? So you do 2 things in one time. You make a carboxylic acid, and you remove the acidic hydrogen, alright? Now, after that happens, you're going to use those electrons and kind of do a quick little SN2 reaction right there. And when that happens, you're going to use potassium terbutoxide, and what that does is that it removes the other acidic hydrogen, but it doesn't do anything else. It's too big and bulky to do anything else, okay? And then you're going to heat up the compound, and whenever you heat up the compound, you remove 1 carboxylic acid and create carbon dioxide, okay? So there you go. Number 5, which is the most acidic hydrogen in the compound shown above, or below, whatever. So you're probably wondering, okay, well, I can make an enolate right here. Yeah, you could make an enolate. I can make an enolate right here too. Okay. But the best one that you can ever do is over here. Or you can do it over here. Okay? And so the best one would actually be 1. Okay? So the answer choice should be A. But why is that? Well, whenever you have 2 withdrawing groups, so let's say over here, whenever you have 2 withdrawing groups, you want your hydrogen to be between them. The reason for this is because if we were to form an enolate right here, okay, so we only have some alkoxides. If we were to do that, you could form an enolate here. You could form an enolate right here, which are double bonds. And then you can also have your traditional double bonds here. And so what I'm saying is, there's a lot of resonance structures. So lots of resonance, lots of res, means greater stability. So lots of resonance means greater stability. Like I said, we can have an alkene over here, or we can have an alkene over there, or we could just have a carbonyl over here, or a carbonyl over there. So we have 4 different places to put our double bond at. Okay? For this guy right here, for number 2, you only have 2 options. You can put a double bond here, or you can keep your double bond right there. The same thing is true for number 3. But for number 1, you have 4 different locations. That's 4, okay? So if your hydrogen is between 2 withdrawing groups, it's going to be really, really, really acidic, and it's going to want to form an enolate. Okay, so that's going to be the most acidic hydrogen. So the answer choice should be A. Okay, now, what about number 6? Well, the number 6 is the same logic. Okay, so it's going to be number 2. Why is that? Well, it's between two withdrawing groups. Now you're saying, Brian, I don't understand. How can you tell if it's a withdrawing group? Well, the simplest way that I know how is, can we form a positive carbocation? So can we make a carbon positive? Well, yeah, I can actually. So what if I made this double bond go towards the oxygen? That will make this oxygen negative, and that will make this carbon positive. And if we could form a positive carbocation, that's going to be a withdrawing group. What about this carbon? Well, what if I made this bond break towards the nitrogen? That's going to make this nitrogen negative, and it's going to make this carbon positive. And so you can see that we made 2 carbocations, okay? And if we can do that, it's a withdrawing group. And if my hydrogen is between 2 withdrawing groups, it's going to be really, really acidic. So the answer choice should be 2. So the answer choice should be 2. Number 7. Considering the highlighted hydrogens, list the following compounds in order of decreasing acidity. Okay, so we're going to write out the numbers. We're going to do 1, 2, 3, 4, and 5. Okay, so this is where our memorization comes into play. I know that number 4 is going to be like the first one, because carboxylic acids are really acidic. They're like -3. They're like -3, okay? And number 5 is going to be like the last one, because those are really basic, okay? Those are like 25. And I know this because of the triple bond, okay? So that's 25. Number 3 should be 16. I know this because they don't allow you to buy alcohol when you're 16. So this is an alcohol group. Okay, you get it? Now it's between 1 and 2. Well, I know that 1 is more acidic than number 2 because this hydrogen is between 2 withdrawing groups. And you remember what I told you about withdrawing groups? If your hydrogen is between 2 withdrawing groups, it's going to be more acidic than just 1 withdrawing group. So I know that number 1 is more acidic. And for memorization purposes, that's like a 9. And this guy right here should be an 18. Okay? So it's like twice as basic as number 1. Okay? There you go. So now if we actually rank them, we would have number 4 first, then 1, 3, 2, and 5. So this is going to be decreasing acidity. Okay, so if we do that, we should have, let's see, 4, 1, 3, 2, 5. Yep, the answer choice should be C. Alright, so this is kind of like a number that you should know. This is 18, and this is 9. So you can see that you actually increase the acidity by twice, right? So this is 16, that's -3, and that's 25. Number 8, which structure represents an ester enolate? Okay, well, number 4 is wrong because these electrons, if they did that, they would form a double bond right there. And that's not right. That's not an enolate, okay? So 4 is wrong. Number 1's also wrong for the same reason, obviously. Now it's either 2 or 3. Well, actually, it's both. Why is that? Well, if I break this bond right here, we're going to form an alkoxide. And then these electrons can actually make a double bond right there. And you would have this compound. Okay, so that's an enolate. What about number 3? Well, it's the same thing. Isn't this the same thing as number 3? Yeah, it is. Is that number 2 has the potential to actually form an enolate. Okay, so we consider it an enolate. It's just like a resonance structure of it. So 2 and 3 are actually right. So the answer choice should be E. Number 9, which of the following is a keto-enolate tautomeric pair? Okay, so obviously we need a ketone, I guess, so that's a ketone. But we also need an enolate, okay? So basically, it's like this. We have an enolate right here. And what if we actually made an alcohol? Okay, well, if I made an alcohol, this alkoxide would disappear and it would actually form an alcohol. Okay, so that's called the enol form, and this would be the keto form. Okay. So this is the enol, and this is a keto. And so you would actually call them the keto-enol tautomeric pair. So that's like an example. What could be an example of a keto-enolate pair in this question? Okay, well, this is obviously the keto form, but the enolate pair doesn't make any sense. Why is the double bond so far away from this initial carbon? No, we want that carbon right there on the base of it. Okay, so 4 is wrong. Ooh. So 4 is wrong. Number 1 is wrong because you don't have any double bonds right there. Where's your enolate? Exactly. And 3 is wrong. This is not good. That's a diol. Ew, disgusting, right? Same thing for number 5 and 4. This alkene is too far away from the initial carbon. So the only one that makes sense would be B, okay, because your keto disappeared and it formed an enolate. So your alkene should be right there, and you can have an alcohol on this pair. Okay, so the answer choice should be B. Number 10, which of these compounds would exist in an enol form to the greatest extent? Okay, so let's actually draw out these compounds. Alright, so these are the compounds drawn out. Okay, so which one would form an enolate more rapidly? Now, if you're looking at answer choice B, that would be the correct answer choice. And of course, because I've said it 3 times already, this hydrogen right here would be between these 2 withdrawing groups, making it more acidic and more available to do enolate formation. Okay, so that should be the correct answer choice. There's a lot of resonance structures that you can do with that one. Number 1 looks weird. I've never seen a double bond to an oxygen before. In that structure, like I've never seen that. It's kind of weird. Well, answer choice C would be wrong. This is kind of like a weird structure to begin with. You wouldn't necessarily see this. Like, yeah, these hydrogens are a little bit acidic, but it's not that stabilized. I wouldn't choose that answer choice, okay? So C is wrong. If C is wrong, then D is obviously wrong. There's only one choice that you can do. That's not good. And these have too many hydrogens right there. So you can make one resonance structure right there. You can make one right here. But it's not as stable, okay? There's too many locations for the hydrogens, okay? So E is wrong. You have too much of a gap between the withdrawing groups, okay? And that's not really good. So E is wrong. And the answer choice would be B, of course, okay? Okay, so number 11, I really like. It's kind of fun to think about it because it incorporates like chapter, I think it was 15, information into this question. Okay, so which of these compounds would exist primarily in an enol form? Okay, well, you're probably saying, okay, well, it's probably E or something. No, it's not. Why is that? Well, first of all, look at answer choice C. We notice that this is almost a benzene ring, okay? And we know that benzene rings are very conjugated. They're aromatic, and so they have a lot of stability, okay? So we always want to go closer and closer to the formation of a benzene ring. Right here, we have a hydrogen, okay? Now, what would happen if I took out this hydrogen, made an alkoxide, and used these electrons to form a double bond? Well, if I did that, then I would reform the benzene ring. I would have a withdrawing group, which is amazing, okay? So you want that to happen. You want this to be stabilized. So if we make an enol, so made enol, and you formed a benzene ring. So whenever you form a benzene ring, you made a lot of stability in the compound, okay? And so if you're enol formation can make a stable compound, then you want to do it. It's always going to go there, okay? So answer choice C would be correct, okay? So this would only make a cyclohexene, or, or diene, I think, which is not that good. It's stable, but it's not the best. Right here, this would just make a cyclohexene, and this would be like over here, okay? So as you can see, they're not as stable as answer choice C. Okay. Number 12, which of these halides is predicted to alkylate malonic ester in the highest yield? All right. So I drew out an example of kind of like a compound that can actually do this. So for instance, they gave you malonic ester. I just drew out this weird anhydride. All right. And notice that I have some electrons right there. So what can we do with this one? All right. Well, this is an SN2 reaction. And we know that SN2 reactions are very sterically sensitive. So if something is too large, then it's not going to want to do it. If something is really, really tiny, then it's going to do it really quickly, okay? So over here for answer choice B, this would not work. Why is that? Well, if this bromine popped off, you would have a carbocation right here. But notice that this would be vinylic, or it would be a vinyl carbocation, and that's really disgusting. If you remember from Ochem 1, you can never do a reaction with aromatic compounds, or arenes, okay? So arenes, they never do reactions because you have an anion or carbocation directly on the alkene, which is really, really disgusting and nasty. No one likes that. It's really icky. Okay, so this is wrong because you have a vinyl. So this is a vinyl compound. So that's bad. All right, and what about number 3, or answer choice C? Well, if this happens, you would have a reaction like this. And yeah, that's primary, but look at what it's attached to. So if you can't see it, you would have a lot of hydrogens right here. Etc. Okay? So you have like a bunch of hydrogens, and these hydrogens are very sterically hindered. They make it unstable. And so why would you put a big bulky base, or sorry, a big bulky group in a tiny location? Why would you do that? That's so many hydrogens in one area. It's not going to want to do that. It's like putting two magnets close to each other when they're on the same pole. They're going to be very, very repulsive, okay? So that's not going to work. And the same thing is true for answer choice D, okay? So the only thing that could work is iodide, okay? So methyl iodo. So when that happens, this becomes negative, and this becomes positive. So we're literally just adding a carbon with like 3 hydrogens on it. So it's very tiny, it's going to work, it's going to do it, okay? So there you go. This is basically you alkylated this malonic ester, okay? So you want something that's super, super tiny because we're doing an SN2 reaction, okay? Something that doesn't have a lot of hydrogens to begin with. So there you go. The answer choice should be A. Okay, number 13, what would be the major product of the following reaction? Notice that we have a base, and we have some hydrogens right here. Okay, so first of all, we're going to do an acid-base reaction with this hydrogen right there. And what happens here is that this hydroxide is very, very hungry, and he takes out this hydroxide, or this hydrogen. Okay? Okay, cool. So that happens. Hope you're having a great day, or school, semester, or whatever, you know. Hope that you're safe as well. So now we have these electrons right there. Well, what if my electrons were like, okay, what if I go here and make an alkene? Well, if I make an alkene, then this center carbon would have 5 bonds, right? And it doesn't like it. So instead, it's going to come out over here to make an alkoxide. Okay? There you go. So that's an alkoxide. And notice that we formed an enolate. Okay, so we formed an enolate. And also notice that this enolate came from the acidic hydrogen. The acidic hydrogen was next to a withdrawing group, aka the carbonyl. Okay, so now our bromines come into play. And our bromines split up. And this bromine is taken by this alkene. And when that happens, these electrons can go back and form the carbonyl. And so your answer choice should be something like 3. Yeah, 3. So that carbon has 2 carbons on it. So it should be 3. 1 is wrong because you have the bromine in the incorrect order. 2 is wrong. I don't know how you have 2 bromines there. And this bromine is on the wrong carbon, so it has to be 3. Which compound would be formed when 2,3-dimethyl-hexanol is treated in a solution of this weird compound? Okay, so here's the structure. Okay, we have 2 and 3. So hexanol means that there's 6 carbons altogether, so 1, 2, 3, 4, 5, and 6. 2, 3 means on the second carbon there's a methyl, and on the third carbon there's a methyl. And al right there comes from aldehyde, so aldehyde. Right? That's how I remember it. So al means aldehyde. Okay, so if we treat this compound with sodium OD, so what's OD? So D in this case means deuterium. So deuterium is very thick hydrogen. Okay, so it's thick hydrogen. And people just use it as like a tagging mechanism because they show up on different isotopes, right? So you can check if this deuterium went to this location instead of this location. Okay, so it's kind of like a highlighter, all right? That's all there is. Just treat it like a normal hydrogen, basically. Okay, so if you have this, notice that there's a hydrogen right here, right? And this hydrogen is next to this carbonyl. Okay, so if I treat it like this, I can actually make this guy. So let's say I treat it with some sodium and OD. Well, over here is going to do an acid-base reaction. So it's actually going to take out this hydrogen. Okay, so now we have this guy. And we have some electrons right there. Okay, so these electrons can actually become an alkene. But whenever that happens, this carbon's going to have too many bonds. It's going to have 5 bonds right here, this carbon. So it's going to split out to make an alkoxide. And notice that we made an enol. So if you made an enol, chances are that you did it correctly. Okay, so you don't have to worry about it. So I made an enol. Right. So now we can treat it with some water, per se. Okay, so if I treat it with water, we're going to have to redraw the structure. If we treat it with water, this is what happens. This guy breaks out towards the oxygen, and this oxygen takes the deuterium. Okay? Alright. And what can happen now is that these electrons on the oxygen can actually reform the carbonyl, right? And this carbonyl can actually, I'm sorry, this alkene can actually become electrons again. And we're going to make some room, okay, because this looks really bad. Okay, so now we have our electrons back. Well, this deuterium can leave. It can leave the oxygen, and these electrons can take up the deuterium. And so basically, after this very fun reaction, we would have this compound. Okay, so there you go. Pretty cool, right? I mean, I would say that it's cool. And so basically the answer choice should be E. Alright, so let's recap. Alright, so first of all, whenever you have sodium hydroxide or something like that, it's going to deprotonate this acidic hydrogen and it's going to give you some electrons. Then you can form the enolate. Okay, you can form the enolate. Now the alkoxide, which is just the negative oxygen, is going to take out one of these deuterium or hydrogens from this water. Okay, now it's going to reform the carbonyl, and whenever that happens, these electrons right here can actually reform. So let's do that. So these electrons can reform, and this carbonyl reforms as well. After that, the deuterium can pop off from the oxygen and be taken by these electrons. So there you go. Okay, so you basically added a deuterium to the compound, which is what you see in answer choice E. Alright, number 15. Number 15 is also an acid-base reaction. Now, let's see if you can do it on your own and see what happens, okay? So we have some hydrogens right there. We have an acid. This breaks out. This bond breaks toward the oxygen takes the hydrogen, and then the bond reforms right there, okay? So actually, the bond doesn't reform, so let's just do this. Now we have our water. Now water is very angry, so it's very angry water, okay? Probably like Dasani or something. Have you ever tasted Dasani? It's kind of weird, like the off flavor. Anyways, waters have flavor, okay? It's obvious. So when that happens, this hydrogen is going to pop off and be taken by this oxygen. And we have this. So we have some electrons, so these electrons will form the enolate. Right here we have a hydroxide, and we also have our acid. Okay, so there you go. That's what happens. Now we have our bromines. So whenever we add bromine, this cool thing occurs. So this becomes negative, this becomes positive. This electron is this alkene is very electron rich, so it's going to take out this bromine. Okay. So there you go. Right. And now our other bromine can take out this hydrogen, and this bond will form, okay? So basically it goes like that, and we have this guy. Okay, so that was the first part. So that was just this reaction, okay? Now we're going to add some very strong base and heat. Okay, so whenever I add a very strong base and heat, what does that remind you of? Well, it reminds me of an E2 reaction, okay? So it's E2 because we have a strong base, we have a metal, see, sodium, so that's kind of like in the 2 dimension. And then we have hydroxide, and we also have heat. So heat means we're going to do an elimination reaction. Okay, so do I make my alkene over here, or do I make it over here? Well, I'm going to make it in the bottom corner, because if I do it upper, this carbon right here would have 5 bonds, and that's very bad. Okay, so your answer choice should be number 2. Right, so answer choice 2 is correct. So this is just an E2 reaction. Oh, that's very bad. E2. So 16, what would be the major product of the following reaction? Okay, so let's start working on this problem. First of all, we would have this compound. Oof. And notice that this carbon would have like 3 hydrogens right here, and they're pretty acidic because they're next to a withdrawing group, okay? So whenever we have a base, we're going to do an acid-base reaction first. All right, so let's say we have sodium and hydroxide. One of these hydrogens is going to come off and be taken by this oxygen. Okay, so now it is like this. Okay, and our iodines can actually separate. So that's negative, and this is positive, and they can be attacked by these electrons. Alright, so that was step 1, okay? So we just kind of removed a hydrogen via acid-base reaction, and we do that because it's really quick to do it. It requires less steps and less energy, so it's very efficient. Alright, and after that we add one of the iodines. Okay, so we still have an iodine right here, but now we have water, or I'm sorry, we have hydronium. So this occurs. The iodine takes one of the hydrogens. Now, why do we do that? Well, we do that because we're going to do an SN1 reaction. Okay, we're going to do an SN1 reaction, and I want water first. I want to add the water into the compound. And to do that, I need to remove one hydrogen. Okay, so this is kind of like a side product. We have HI now. Okay. And now, this iodine is going to pop off to make a carbocation. And this oxygen is going to attack that carbocation. That's kind of like the trick in this question. Okay? Alright, so now we added the water. Alright. And now we have iodine just floating around, and this hydrogen can pop off from the oxygen and be taken by the iodine, and the side product will be HI again. Hence, we only have this compound right now. Let's see, some alcohol. And we also have 2 HIs. Alright, so the answer choice should be B, right here. Now let's kind of review it. First of all, whenever you have some acidic hydrogen, you're going to do an acid-base reaction with the sodium hydroxide, or an acid, right? That's going to come off, and you're going to add your iodine, or whatever halogen you have right there. Afterwards, one of the leftover halogens is going to react with your acid to make this into a water. And now the water is going to be added into the compound via an SN1 reaction. It's going to deprotonate and give that hydrogen to the halogen that you added. And that's basically it, okay? So, pretty standard. Which compound could be subjected to a haloform reaction to produce M-chlorobenzoic acid? Okay. Very, very cool. Alright, let's do this. Okay, so what kind of reaction is this? In class, or in life, you're going to learn that this is a haloform. This is going to be a haloform reaction. And basically what a haloform reaction is that you can treat this compound with the base. Why do we want a base? Also, this is a chlorine. But why do we want to treat this with a base? We want to do that because these hydrogens right here are very acidic because they're next to the carbonyl. And so if I treat this with a base, I can just pop off one of these hydrogens and give it to my oxygen, right? Now we're going to have some electrons right there, right? Okay, well, this bond can break towards the oxygen and you can form an enolate. So if I did that, we would have this guy. Okay, and we also have H2O. Okay, now my bromine, or my halogens, let's say bromine in this case, can come in. Actually, let's use chlorine in this case. So chlorine can come in, and this breaks out. And now we have a chlorine. Okay? So that happens, but we can do it again and again and again and again. We can actually do it 2 more times because we have 2 more hydrogens, okay? And so let's say that we have sodium hydroxide again. And it's going to take out this hydrogen and blah blah blah. It goes through the enolate, the chlorine comes in, attaches itself, and then it does this again. And if you do this this process like a billion, trillion, cajillion times, this basically you chlorinated it, or I should say you halogenated it. So you exhausted your acidic hydrogens and you replaced all your hydrogens with chlorine or bromine or some type of halogen. That is a haloform reaction, okay? Why do we do that? Well, we do that because this is a very, very good leaving group. Now let's say that this chlorine, or this carbon leaves, okay? And we treat this with sodium hydroxide. Well, all that happens is that we form a carboxylic acid. Very cool. Okay, so that was it, all right? We're basically finished. So, yeah, that's a haloform reaction. The haloform reaction just means that you treat this carbonyl with hydroxide, and you're going to deprotonate one of these hydrogens, and then you're going to add your halogen to that area, okay? And you do this until you run out of hydrogens to take out. So basically, you put in a bunch of halogens into that area. Afterwards, that carbon could come off because it's a great leaving group. The negativity of the carbon is equally dispersed amongst the halogens, okay? And then you just treat it with a base. The base is going to come in, do a simple reaction, and add itself to the compound. So basically, you made a M-chlorobenzoic acid, okay? So answer choice 4 would be the correct answer choice. So D. Right here, you don't have a carbonyl. Bad. Over here, you have too many carbons. That would give you like an awkward compound. Right here, that's a carboxylic acid and no chlorine. Ew. Disgusting. And right here, yeah, there's no carbonyl. That's just an alcohol. That's bad. So answer choice D would be your correct answer choice. 18. What would be the major product of the following reaction sequence? So first, we're treating this compound with LDA, which is lithium diisopropyl amide. Okay, so what does that do? Basically, it just makes an alkene. Okay, so you know me, I really kind of like condense information. I'm not showing you that reaction. I think it's pointless. I just want to show you what it does, okay? Basically, this is the new kid on the block. This is the new kid. Like, his parents just bought a house on the cul-de-sac. He's fresh off the house. He doesn't know what to do. He's trying to make friends. People think he's a bit weird. But eventually, he grows on you. Like, you ever seen The Sandlot? Yeah, the new kid. So, LDA doesn't know what he's doing, and he just tries to fit in. Sometimes he's a bit unstable in his reactions, but he does what he does, okay? He's very strong. It's a very strong base, but it's very unstable, okay? So, essentially what happens is that since he's so new to this reaction business, he doesn't know what to do. And so he's going to form very, very unstable alkenes, okay? So he forms very unstable alkenes. And this is what happens. Essentially, he makes this alkene. Disgusting, I know. Because essentially, you want to make the worst alkene possible. The best one would have been over here, right? We would have made an enol. But for LDA, he does it so quick and so fast that it's very unstable. So that's what you're going to have after LDA happens. You still have the carbonyl, but you also have an alkene, okay? So this doesn't change. This stays the same. Stays the same. Now let's draw a heart because I haven't drawn a heart in a couple of videos. Okay, so that stays the same, right? And afterwards, we're going to treat this with some of this guy. So we go 1, 2. Then we also have an iodine right there. Well, this iodine can come off being negative, and this is going to cause a carbocation. This alkene can actually take that carbon. Okay. Also, I've watched like The Sandlot like 13 times. It's a great movie. Okay, so now we have this carbon, so we go 1, 2. And that's it. That's all we have. So what is the correct answer choice? Well, the correct answer choice would be 1. So here's our initial carbon, and here's our C2H5I. Okay, so this is what we added, right? Again, LDA just makes the most unstable alkenes, so LDA, lithium diisopropyl amide, makes unstable alkenes. So it makes very bad alkenes, and here we go. After that alkene is formed, you're going to basically use that alkene to get the compound, okay? So again, PCC on alcohol just makes it into a ketone. So for number 19, we're doing that question now. You just made a ketone right there. This doesn't do anything. It just kind of like facilitates the reaction, okay? So kind of like when you use Grignard reagents with ethers, the ether is just there to facilitate the reaction. So don't worry about that weird guy, okay? Don't worry about that. Now we will form LDA. Again, where am I going to form it? Well, Brian, I'm going to form it on the worst possible location that I can do it on, okay? Okay. So what's the worst possible location? Well, if I form it here, that's going to have like, it's going to be di-substituted, which is stable, pretty good, but I don't want that. I don't want it to be di-substituted. I actually want it to be really, really unstable. So that's where I'm going to put my alkene. I'm going to put it on the right-hand side. Afterwards, we're going to react with C3, CH2, and bromine. So this guy pops out. That's negative. This is positive. This double bond takes the carbon. And now we have this compound. There you go. So your answer choice should be 3. Okay, so answer choice C. This right here, this came from forming your alkene over here. So that's how number 4 was occurring. Sorry, so let me reiterate. So number 4 is wrong because that comes from a more stable alkene, which is bad. LDA makes unstable alkenes, okay? So 4 is wrong. 5 is ill. I don't know. That's wrong too, so the answer choice is C. A compound reacts with phenylhydrazine and gives a positive iodo test, or iodoform test. The compound could be which of these? Okay, so iodoform is, it's going to check for these compounds. It's going to check for R right here. So, and this guy, okay, but it can also give a positive test results for acetaldehyde, so like this. And notice that this is basically like a very tiny molecule, so there's nothing else attached to that carbon. There's just hydrogens, okay? That's acetaldehyde. Anyways, this iodoform is going to give us a positive test result for ketones that have acidic hydrogens. So these hydrogens are going to be very acidic compared to everybody else. Okay? And it also gives a positive test result to alcohols that have, again, acidic hydrogens. And essentially an iodoform test, if it's like a clear liquid, but if you put your compound into the test and you get like a solid yellow substance like chalk, it looks like chalk, then it's a positive test result. Okay, so over here this is an aldehyde, so this is an aldehyde, and we know that this is not going to work. You're probably saying, well, this is an aldehyde. Well, yeah, but it only has 2 carbons. This one has a bunch of carbons, and that's not going to be a very good test result. So this is a fail, so this is wrong. B is also an aldehyde, but again, you have too many carbons. See, if you got rid of these carbons and you only had this compound, then yeah, that would give you a positive test result, but there isn't. Now over here is an alcohol. That's pretty good, but notice that there's an alkene on it. And alkenes are not very good when they're paired with alcohols. So this is not going to give you a positive test result because of the alkene. Okay, that's wrong. Now D would be the correct answer choice because it is a ketone. And notice that we have some acidic hydrogens right there, and there are no alkenes. So this would be a very good substance to use the iodoform test on. Right here on answer choice E, this would be wrong because, yeah, we have a ketone, but it's in the middle of the compound, and we know that's not good. So these are not very acidic hydrogens, okay? They're very bad hydrogens. So you want your ketone to be on the very edge of it because you want these acidic hydrogens, okay? So again, the iodoform test only works for ketones that have 1 carbon to the other side of it, okay? So it works for this guy, it works for alcohols, and it works for acetaldehyde. Only for acetaldehyde, okay? And methyl ketone, whatever that is. So the answer choice is D. Number 21, what would be the major product of the following reaction sequence? Okay, so we're treating this bromine with magnesium, and whenever we have magnesium right there, we can just ignore it, and we would have this compound. Now we're treating with we're treating it with some carbon dioxide. I don't know why I kind of like blanked out. So here's my carbon dioxide. We can go here, that's positive, gets attacked. see. There we go. Okay. And after that, we're going to do a very cool reaction. Okay, so it's a very cool reaction, and I have to clear out the screen to show you. So this reaction is called a Hell-Volhard-Zelinsky reaction. And essentially, you want to use a carboxylic acid, so must use. It says must use. Carboxylic acid, so we're going to call it carbox acid. And phosphorus. And phosphorus. Also must have a halogen. And the end product is essentially this product right here. Okay, so that's the Hell-Volhard-Zelinsky reaction. And essentially, you want to look out for this phosphorus right here. So this is called red phosphorus. That's red phosphorus. And you have a halogen right there. Now, you can do it with chlorine, you can do it with bromine. If you do it with bromine, you can use PBr3 and Br2, okay? So all that we did was said, so let's pretend that we're in the lab. We're like, okay, well, I want a carboxylic acid, but I want to make that a really strong acid. How do I do that? Well, first I make a Grignard reagent, and I'm going to treat it with carbon dioxide and acid. So all that does, it makes a carboxylic acid. That's all it does. So that's what the whole chunk does. It makes a carboxylic acid. And now on the exam, you can see, okay, well, we have phosphorus and we have some sort of halogen. Well, I know that this is red phosphorus, and whenever I see red phosphorus, I'm just going to make it into a Hell-Volhard-Zelinsky reaction, or HVZ. And all that does is that it adds your halogen to the alpha carbon. So this is the alpha carbon right there. And this makes the overall acid very, very strong. Okay, so that's the Hell-Volhard-Zelinsky reaction. Okay. So what is your answer choice? Well, let's see. Your answer choice should be B. Right there. All right. So that's not too bad. Pretty fun. So yeah. What would be the major product of the following reaction sequence? Okay, well, whenever you treat an alcohol with PCC, you're going to get a ketone, especially if it's a secondary alcohol. You're going to get a ketone. And afterwards, you can use LDA on the ketone to make an alkene, which is very unstable. So it's going to go over here. Now that alkene is going to react with this compound. And it will give us the following answer. Okay, so your answer choice should be A, right there. Simple. Okay, so now what would be the product P of the following reaction sequence? So whenever you treat it with sodium methoxide, you actually rip off one of these hydrogens. Okay, you actually rip off one of those hydrogens and make some electrons right there. And then this guy, pH, Br, that can be attacked. And we go to carbon, and then pH. And now we treat it with sodium hydroxide, which makes it like this. Okay. And now we're going to treat it with some heat. And whenever we add heat to this reaction, we actually take out one of the carboxylic acids, or the only carboxylic acid. Let's do this. So we go carbon, then pH right there. Okay, so it wasn't too bad of a reaction. It should be, I believe, 3, right? It's looking like 3. And so essentially, if you see this on the exam, just notice that your sodium ethoxide is usually paired with sodium hydroxide. So you can eliminate this compound and replace it with an alcohol. And then heat is going to take out this carboxylic acid, right? Now the sodium ethoxide is going to take out one of these hydrogens. You can add whatever is in the bottom to this carbon, and yeah, that's it. It's a very simple reaction mechanism. So answer choice is C. Number 24. What is the product L of the following reaction sequence? Okay, so I drew this out, and notice that we're reacting it with sodium ethoxide. Okay, so sodium ethoxide, you know that it's going to pull out one of these hydrogens, and you usually know that it's paired with sodium hydroxide. Okay, well, let's do that really quickly. So sodium ethoxide takes out one of these hydrogens and leaves the electrons, and now we react it with ethyl bromide. So that's negative, this is positive. These guys attack that carbocation. We now have this. Okay, there we go. And now we're going to use potassium tert-butoxide. And potassium tert-butoxide just takes out the remaining hydrogen, but it doesn't leave anything. It just leaves the electrons, okay? So it doesn't add anything to the compound. It just leaves the electrons. So this is our potassium tert-butoxide. Okay, so that's our potassium tert-butoxide. It takes out the remaining hydrogen. And now we can add this methyl iodine. Okay. There you go. And now we add sodium hydroxide. So all that does is that it removes the ethyls from the oxygens and make them into alcohols. So basically carboxylic acids. And after that we add some heat and some acid, and we will get carbon dioxide. We only cleave off one carboxylic acid. Okay? Just one. So here's our methyl group. And then here's our ethyl group. Okay. So overall, the answer choice should be 4. So here's our carboxylic acid, our carbon that has a methyl on it, and then an ethyl as well. So the answer is D. I hope that this video helps you out on your exam. This is the last Ochem video for this semester. I hope that you had a lot of fun hanging out with me. It means a lot when you watch my videos. I just want to say thank you for staying with me. You're a great person, and I hope that you and your family are safe. Remember that I believe in you, and you can do whatever you want in life. You can succeed, and just know that I'm always proud of you. And I love you. So again, thank you so much for being there with me. Just have a great day. Bye. I almost forgot to mention that Gizmo wanted to say that he loves you too, and he hopes you do well in life. Okay, so goodbye, and have a great day.